Microsystems for Space Science, presented by Antonio Ricco.
Thank you.
Get you hooked up. Okay. Should get plugged in on this. Let me just switch. Yeah, there you go.
It's there.
There we go.
No worries. Yes, a little water. Well, good morning, everyone. It's a real pleasure to be here today and talk about something completely different than the electrochemical science you've heard about so far. My roots are in electrochemistry. Like Professor Crooks, I spent some time with Mark Wright and getting my PhD, in my case, at MIT. But I've moved on to various other things, though actually electrochemistry still is a big part of some of my science. Today, though, I'm going to tell you about how we do biological science, analytical biochemistry, if you will, in outer space using small satellites. And I'll point out that there's a very large team of people that contributed to this work. About a third of them are scientists, about two-thirds are engineers, as you might expect. These projects typically take us a couple of years from concept on a paper napkin to having a satellite in outer space and getting biology results back. There turns out to be, though it's not the plan when we start, a lot of science experimentation and experiment development that happens in parallel with the engineering. This is called doing things the dangerous way. But usually we end up with a science experiment that works. These small satellites, we've launched several of them now. One did gene expression, one looked at dose dependence of pharmaceuticals. Another one that I'll tell you about today was for astrobiology experiments, and I'll tell you what that means, looking at survival of organisms in organic molecules. And they're all about a foot long, so the size of a large loaf of bread, and weigh in at about 5 kilograms. OREOS is the organism organic response to orbital stresses. They're called nanosatellites not because they're nanometer scale. Dick Crooks pointed out to me recently that we were actually doing nanotechnology together in some of our collaborations before we knew it was nanotechnology, so it seems more important now. And we were doing molecular layer deposition before we knew it was that too, so it even seems better. And actually, I just need to digress for a minute, but they're called nanosatellites because conventional satellites are the size of a small car. Microsatellites are anything under 100 kilograms. And so a while ago, someone decided a nanosatellite was anything under 10 kilograms. And yes, there are picosatellites. Those are under 1 kilogram. But I'll tell you about nanosatellites today. But before I do, Dick and I have done a lot of wonderful things over the years, co-founded a Gordon conference, co-edited a journal article, started an NSF workshop, published about 20 papers together, and spent some time on various holidays. Here he is with his wife Julie in the Japanese tea garden in San Francisco around the time that he did a sabbatical leave with me at Aclara Biosciences when we both had some experience in industry. Actually, we went on to start a small company in our spare time. That's gone off in other directions now. And I want to show you one other time we got together. This was in Tuscany, Italy, for a Gordon conference at this lovely villa in the Tuscan Hills. And here we are, Dick and myself and his wife Julie, my wife Georgia, sitting at a lovely dinner, looking happy, and actually we're looking kind of relieved if you look at the expressions on our faces. And the reason we're relieved is because none of us is in an Italian jail or recovering in an Italian hospital from gunshot wounds. So there was a little, as we were driving sort of over this ridge to the restaurant from the conference site, we came upon this fellow or someone like him. Actually, there were half a dozen or so Italian policemen standing by the side of the road with a couple of cars, just chatting and smoking and looking very nonchalant. One of them was standing a little closer to the shoulder of the road than all the other Italian policemen, and he had something in his hand that looked sort of like an oversized ping pong paddle. Dick was driving at the time, and as we drove past, it was a small country road. We weren't going very fast. He sort of casually raised the paddle to about 45 degrees, and we drove on. Someone noticed that, maybe my wife, Georgia, who's from Europe, or it might have been Julie, and said, "Dick, did that mean something? Aren't we supposed to stop?" And Dick and I were chatting away. And at some point I turned around and noticed a number of the Italian police officers scrambling to their cars and taking off in hot pursuit. And at that point, all of us told Professor Crooks he really needed to stop the car immediately. So he did, and a very short time later, a bit out of breath, this gentleman or someone like him appeared at the window of our car, no longer with the ping pong paddle in his hand, but with a pistol in his hand. And the pistol was also sort of at that nonchalant 45-degree angle, but a little closer to horizontal. And we were pretty taken aback. Now Dick is really never flustered by anything. He calmly got out his Texas driver's license and very politely handed it over to the policeman, who was scolding Dick and the rest of us in Italian, but we didn't really know how we were being scolded. And Dick always knows what to say at the right time. So as he handed over the license and the policeman started to peer at it and wonder what was going on, Dick pointed at himself. He said, "Estupido Americano." And the policeman at that point, you could see his shoulders slump, and he sort of looked like he'd just lost his favorite dog or something. Looked really depressed, and he looked at the license again, shook his head a few times, sighed again, handed the license back to Dick, and just sort of said, "Goodbye, arrivederci." So anyway, there we are all enjoying our dinner. Okay, so back to space science. I'm going to tell you today about astrobiology and space biology. Astrobiology is very fundamental science, looking at the origin, evolution, distribution, and the future of life in the universe. And sort of to break this down a little further, one goal is to look at the details and the distribution of prebiotic chemistry, the chemistry that gives us the chemical building blocks of life. And one of the payloads on the small satellite I'll tell you about today, called SIVO, does just that. Another goal in astrobiology is to look at the potential for existing life from Earth, or if there is elsewhere, to adapt and survive in environments beyond Earth. And our second payload, called CESLO, does that, and I'll talk about that. Another goal is to look for signs of extant or extinct non-terrestrial life. SIVO does a little bit of that in the sense that it's looking at longevity of biomarkers that could be molecules that indicate life once existed somewhere. Find habitable environments in our solar system and beyond. We're not doing any of that in this small satellite. So again, the reason is just very fundamental science and understanding where we all came from and where we might be going. The other sort of science that we do with these small satellites I won't talk about explicitly today, but that's fundamental space biology. And that's much more concerned with taking our own biology from the Earth, whether it's humans or small model microorganisms, into space, and looking at the effects of reduced gravity and radiation on them over the short and eventually the longer term. And why do we do that? Well, human space travel is still something that happens. People spend long periods of time in microgravity on the International Space Station. There's the possibility someday of a base on the moon and at least longer term lunar habitation before that happens. And so we need to understand these biological effects. We also find that space can be an accelerated testing platform, if you will, for certain kinds of effects that happen in space. And those are things like loss of bone density, which happens at a rate of 2% a month in some of your heavy load-bearing bones when you go into space, immune stress, muscle atrophy, and so on. These things happen at a pace in microgravity that you just can't duplicate here on Earth. So it's a good way to study those mechanisms. But today I'm really going to focus more here. All right, so why do we do this in such small satellites? Well, obviously part of the answer is because we can. The sorts of technologies that most of us have been involved with for much of our careers, in everything from microfabrication and bioengineering of organisms to optics and sensors and microelectromechanical devices, microfluidics, all of these things, together with engineering advances in electronics and communication, let us do things that formerly would take a whole laboratory in something quite small, something the size of a 10-centimeter cube, or in our case, 3 10-centimeter cubes linked together. Access to space is the second very important reason We often fly these, we almost always fly these as what are called secondary payloads. So we hitchhike along when a communications satellite or some other commercial satellite is going into space, or a military satellite. Because we're so small and weigh only a few kilograms, we can pay a piddling sum of a couple $100,000, which really is not that much to do outer space science, and ride along with those. And there are many launches from the U.S. and Russia, Europe, Canada, India, Japan, other nations. So it's possible not to just do a one-off experiment, which is what most of space science has been till now, but to repeat the experiments and learn. It's a wonderful education vehicle. These small satellites, because they're inexpensive to develop, are being used by about 100 academic institutions around the world to train students, and actually many of those institutions have flown small experiments in outer space. They run autonomously. That means we don't have to take up the time of the astronaut crew, and that actually lets us do, in some cases, more complex experiments than you can ask a crew member reasonably to do in microgravity, and sometimes gets you ahead in the queue. We can also take these technologies and migrate them to other platforms, to the International Space Station, to landers, basically payload instruments for landers that will go to the Moon or orbiters, Mars, and elsewhere. Okay, so now to get a little more specific about the OREOS system. In the space parlance, the bus is the sort of the brains and the power control center of everything. This has radio, batteries, data handling system, and so on. And this bus is a 10-centimeter cube, and that's then joined to two other 10-centimeter cubes. So one of them will do our biology experiment. The biology payload houses two different biological specimens, in each one of these things called a bioblock. And those three bioblocks are there so that we can look at the growth of the organisms at three different times. So what we're trying to do is look at, as a function of time in outer space, how does the viability of these organisms change? Does the space environment, the radiation, the microgravity, make them less viable as they spend more time in space? And we'll test this from time 0 up to 6 months. We use optics in these systems to measure the growth and metabolic activity of the organisms, and I'll tell you more about that. So the second experiment, in its own 10-centimeter cube, is basically an organic photochemistry experiment, and it's looking at organic molecules that are either candidates to be prebiotic chemicals that could be the starting point for life, an amino acid, a polyaromatic hydrocarbon, or they are so-called biomarker molecules, molecules that if we found them away from Earth, we might suspect that life might have once existed in that environment. So those are things like an iron porphyrin and a quinone. Those are supported in little tiny cells that sit right on the outer surface of this small cube, and each of them can be in its own microenvironment, either argon to simulate space vacuum, or a humid environment, or oxygen, or carbon dioxide, so it looks like the atmosphere of Mars. And we characterize those films as a function of time on a daily to weekly basis using UV visible spectroscopy with a spectrometer that sits down here in the bottom third of this cube and read each of those films. And around it all, of course, are solar panels, so this is all autonomous and self-contained. So here's an engineering exploded diagram of what went into space. Here you see the organic payload, the biological payload that grows the organisms. This one is the organic photochemistry experiment. And the organic films sit here in this carousel, which rotates around and lets us use the spectrometer to look at them one by one. Over here in the bus, you see some lithium-ion batteries, the same ones in your laptop. It has actually two radios to make sure we get to talk to it. One of them is a UHF radio with this little piece of tape measure that acts as its antenna. And that actually allows not only our own team, but also ham radio operators, amateur radio operators around the world to pick up the signal from our satellite. And we actually got people from 25 countries submitting 1,000 data packets in total to us over the couple-year lifetime of this experiment, where they could go to our website and learn how to find the right frequency and get the data back. So that's a wonderful outreach, and people can really see what's going on. The workhorse radio is what's called S-band, and it actually uses the very same Wi-Fi that if you're connecting with your laptop to the Wi-Fi network here you're using. It's got a little bit more power, though surprisingly not that much more. And that's what lets us send down the data and actually send commands back up to the satellite and control them. And this antenna has to be pointed approximately in the direction of the Earth so that it can communicate with a pair of 3-meter dishes at Santa Clara University, where the operations are done for this by students and staff. In order to do that, there are actually some magnetic rods that sit behind the solar panels and point the end of the satellite towards the north magnetic pole, which gets this antenna aimed close enough to the field of view of these dishes that we can track it as it goes overhead. Okay, so this launched from Kodiak, Alaska in November of 2010. One unusual hazard for us was there are Kodiak bears wandering around the launch site there. You really do have to be careful when you get out of the vehicle, but nobody was eaten and the bear did not carry off the satellite. That would have been embarrassing. Here's the one that's in space now. It's actually still up there. It's been up now for about 3.5 years. And from Earth, we watched remotely, by way of this little antenna, how the biological organisms fared and how the organic molecules fared for up to 1.5 years in space as they were exposed to that environment. Now, what I didn't say explicitly, but you'll obviously recognize, the organic films are sitting here right on the outside. They're actually on the inside of magnesium fluoride windows, but that allows the full UV spectrum through to do its worst. Okay, so the Cesslo payload, this one behind that white panel, looked at the growth and metabolism of a pair of organisms using optical density and colorimetry and a crude form of spectroscopy, actually, and the organic photochemistry we did with SIVO. Just checking the time there. So at present, this is in an orbit of about 635 kilometers. It should be down in about 22 years. All of it burns down when it re-enters. All of it burns up, I should say, when it re-enters, with the possible exception of some little titanium screws that fasten on the solar panels. Titanium's refractory enough, and those are small enough that they may survive. So if you ever see a titanium screw on the sidewalk somewhere, it could have come from our satellite. But don't worry, there are much bigger things falling out of space all the time that you've got to worry about more than these little tiny screws. The environment this satellite is in is fairly aggressive. It's up at 650 kilometers when it started. It's come down a bit now. 72-degree inclination means it's orbiting between the Arctic and the Antarctic circles essentially every 90 minutes. And so the biology was subject to not quite microgravity, but about 10 to the minus 4 times the gravity we experience here on Earth, and got over a gray of total dose across 6 months, which is quite a dose. The organics are exposed obviously to the full UV spectrum from 120 to 2800 nanometers, so the Lyman alpha line is there. 10 electron volt photons, those can do some really interesting photochemistry. And it's in the sun about 30% of the time. So over the 6-month first nominal mission lifetime before we realized we could go on for 17 months, it got about 3,600 hours of solar exposure. And because the films are so close to the surface of the satellite, they got a 55 gray, which is quite a dose of ionizing radiation over 12 months. We also have onboard radiation sensors to track what's going on. Those are called RADFETs, and we include those at various points in the payload. Okay, just to point out, a lot of the space biology that's done and other space science experiments that are done these days is done in the International Space Station. It's at a lower orbit, which is a good thing for the astronauts. The total dose is about 15 times less at ISS than our satellite is getting up where it was. That was a concern for us because the electronics are not special radiation-hardened electronics, but we did a lot of ground testing and found we could get by with commercial electronics, provided we took some other measures to make sure the satellite was at least resilient to radiation, if not radiation-proof. So there are a number of commercial sensors that measure pressure, temperature, humidity, radiation, as I mentioned, light intensity, actually another temperature measurement using a thermopile, and those are all incorporated in this, so I won't take time to talk about those today. So let's talk about the biology experiment in a little more detail. We flew 2 organisms. Bacillus subtilis is a very common spore, and it's one of the ones that's always an issue that can wind up in spacecraft, even if they're well sterilized. Between mating metal surfaces, there's always the possibility that some spore-forming bacteria are there and travel to other planets. So it's of interest from the standpoint of ways that you might contaminate another planet. But it's also of interest because it's so robust and so hardy. If anything's going to live for the long duration in space, maybe protected by a piece of rock, this would be it. Halorubrum caoviatoris, this is an extremophile. This lives, or a halophile, this lives in salt flats. And that's of interest because when you look at the history of Mars, for example, which was now believed to have been quite wet 3 billion years ago, as it dried up, it became very, very salty. And so things that can live in high salt concentration are important because they can live in Dick's desalination system that he told us about, but they might also be able to live on other planets. So what we do is for each organism, we studied a wild type and a radiation-sensitized mutant. We dried them on the walls of microwells, and we rehydrate and feed them at 3 time points in outer space, 2 weeks, 3 months, and 6 months after launch. We grow them at 37 degrees. The Bacillus subtilis takes about 3 days to grow. The Halorubrum takes 17 to 21 days, and watch the development. We monitor, as they're growing, transmittance at red, blue, and green wavelengths, so this is a very crude sort of spectroscopy. And we include a metabolic indicator dye called Alamar blue, which changes color from blue to pink as the organisms metabolize. And so that optical density lets us track the density of organisms as they grow, and the Alamar blue lets us look at their metabolic activity. As I said, there are a number of sensors, half a dozen temperature sensors, humidity, radiation, and so on included. Okay, so taking a little closer look at the heart of this, the microfluidics. The wells start dry with the organisms dried on the walls, as I mentioned. The nutrient medium is pushed in when it's time to start the experiment. The air goes out through a layer of something a lot like Gore-Tex, a porous Teflon membrane, essentially, and the wells are filled up. The organism will then start to grow. It's held at a constant 37 degrees by an overlayer that's some layer of heating tape and a metal aluminum plate to spread the temperature uniformly. And on top of that is our optical system, rather simple. We have a 3-color light-emitting diode, and down here a broad spectrum detector, and the light red, blue, and green comes down one color at a time, and we detect the intensity at each wavelength. So that happens in each of these 3 bioblocks, as we call them. Each of these has 12 wells of the sort I just showed you in cross-section. Integrated valves turn on the flow of nutrient when it's time to start. One medium for the first organism, a different medium for the second one. The system looks like this. It's made of a polymer called Ultem. That's why it's this kind of dark yellow. We've also made them of polycarbonate, and this is a easier to look at cross-section. There you can see the 2 valves, and these are the reservoirs that contain the nutrient, and the valve opens, lets it flow into the wells. Biocompatibility is one of the hardest parts about doing this kind of experiment in outer space. We need organisms to survive, including the time before it launches and our time in space, of 60 weeks and longer. Actually, you've already got 24 weeks to go out to, or 26 weeks to go out to half a year. So this additional time is for time on the launch pad. And without going into great detail, we have to split the materials into categories according to whether they contact the organisms or whether the growth medium contacts the material and then goes in. And we tested a couple of dozen materials for this over 60 weeks. And when you find a bad one, this is one of the risky parts. You've got to figure out how to substitute a good one for it without setting your engineering back to square one. So that was a challenge, but we managed to do that. We cheat a little bit by putting activated charcoal in the form of a cloth that's sold commercially, and put quite a few square centimeters of that. That tends to pull out volatile organics that might damage the biology, and that really helps. Okay, so here's what the unit looks like, one of the bioblocks with its temperature control. 3 of these are sandwiched together to start to build the internals of the satellite. And then it's all wrapped up in a 1-atmosphere container with a thinned region so that the space radiation can get in and get at the biology. Our optical measurement I mentioned, so we're using this dye called Alamar blue. In the oxidized form, which is how it starts, it's this nice blue color. When it gets reduced by common electron transfer components of cellular metabolism, things like NADH, FADH, some of the cytochromes. When it gets reduced, it turns from this blue color to magenta, and then actually it can be further reduced if there's enough food around for the biology. It'll get reduced to a colorless form like that. And so you go from the dashed line here, the oxidized, to the solid line here, the reduced, the magenta, which also happens to be fluorescent. And so we monitor the oxidized form primarily with red light. We monitor the reduced form primarily with green light. And the blue wavelength lets us get at the optical density. And we actually, as you can see, there's spectral overlap in all cases. We do a three parameters and three unknowns fit and pull out the amount of oxidized, the amount of reduced, and the optical density. You see the 3 units kind of stacked up here ready to go. All right, so here's some of the data from outer space and from the ground. So we're always comparing ground and space. So the space flight is the darker colored curve, the ground is the lighter colored curve, and this is the green wavelength at 525. So what you're seeing here is the pink color growing in, so increased absorbance. Then the pink actually starts to turn colorless, the pink color goes away, but the optical density continues to grow, and so of course green light is also sensitive to light scattering, and this heads back up again. And we found this sort of characteristic signature very, very nice to watch and let you monitor what's going on. So that's what I'll show you today for sake of clarity and time. And you can see I'm showing you the response in space and on the ground for the wild type here, and then space and ground for the mutant, which is a bit more radiation sensitive down here. You can see they all look pretty similar. The space ones almost look more similar, and the ground ones almost look more similar. So there's not a big difference between space and ground, but that's only 2 weeks after launch. Then here's space flight and ground after over 3 months in space, 97 days. And again, it's remarkable actually how similar all the curves look 3 months later to how they looked at 2 weeks. There's really very little change in either the wild type or the mutant in its metabolic characteristics and its overall growth pattern. The interesting things come at 180 days, and something clearly happened here. Well, unfortunately, we can't unequivocally ascribe what happened to radiation, though it certainly could be a component of this. But we know that this satellite was in a very challenging orbit where sometimes it was in the sun night and day for 24 hours. And though our thermal engineers did their best to paint it the right colors, there was no active cooling on the satellite, and it got warm in there. We estimate the bacteria got up, the bacillus got up to something like 42 degrees C, and that affected its viability. This is the important reason that you do a ground control. So we did the ground experiment, and we tried to reproduce as best we could the thermal history that we saw reported from space. And indeed, that if you compare this ground growth curve to that one, you see it has slowed down quite a bit, but it hasn't slowed down as much as the space flight. And we're still trying to decipher right now whether that's the combination of radiation and thermal effect in space, or if it's simply that the thermal environment was more harsh in space than what we managed to replicate on the ground. But the point is, overall, it's a really nice comparison experiment. You've always got to do the appropriate controls to have a hope of figuring out what's going on here. So these organisms can survive a long time, but obviously the thermal environment's very important, not just radiation. So let me tell you in the last few minutes about the second payload called SIVO. That's Space Environment Viability of Organics. And again, we looked at an amino acid, we looked at a polyaromatic hydrocarbon. These are potential carbon source and obviously building blocks for life. We looked at an iron tetraphenyl porphyrin. We looked at anthrorufin, a quinone, as things that might be signatures of biological activity. And really, we're just looking at their stability. We're trying to see how long could they last in space. We put them in microenvironments simulating vacuum, just pure argon, or in contact with silica to simulate contact with the mineral surface, or in a CO2 ambient like Mars, or in a humid environment like you might find on Europa or somewhere where there's a lot of water. They got exposed, again, over this very broad range of solar wavelengths for nearly 4,000 hours. Every day initially, and then every couple of weeks, we measured the UV-vis spectra of these 18 films using the sun as our light source, and we can use the solar spectral features to calibrate the wavelengths. And this one has a number of sensors as well. Okay, so here's a close-up of one of the sample cells. The organic film is this little blue film here sitting on a magnesium fluoride window. The sunlight comes down for making the UV vis measurements through a diffuser and some baffles, collected by an optical fiber off to the little spectrometer, which is very much like the ocean optic spectrometer some of you, I'm sure, have used, but it's a space version that has a much better temperature stability coefficient. These cells are organized, 24 of them, in this carousel, which lets us read them out one by rotating this with a motor down inside the spacecraft. We have sun angle intensity sensors to tell us when the satellite is facing the sun so that we can take spectra, and radiation sensors here again. And there's just a cross-sectional view. We didn't have room for optical switches here, so the way we could get 24 samples in was by having two rings of samples, one with a pickup there, the other one with a pickup there, and the wheels arranged so that only one or the other of these two optical pickups is aligned with the sunlight in any given time, any given wheel position, and the other one's staring at the back-painted black-painted back surface of this wheel. So that's your very crude optical switch. It works quite nicely. There's some engineering diagrams just showing you how everything fits together, again in this 10-centimeter cube and one of the sample cells, and a photograph of the unit being tested on the ground before going into space. And now some spaceflight results. So this is for isovial anthrene, a polyaromatic hydrocarbon, 34 carbons, I believe. And these are ubiquitous in interstellar space. They do survive the deep space radiation conditions actually pretty well, including lots of UV exposure. What you can see, though, is that they don't like humidity when they're getting bombarded by UV. So if you look in argon, there's very little change from 2010 to 2011, almost a year later. Same thing in contact with silica. With CO2, not much change either, even though there's a little bit of oxygen in this. And then in the case of relative humidity, you make hydroxyl radicals. Those come up again and again in interstellar chemistry as well as terrestrial, and those will slowly destroy the film. So it's going to be relevant whether these things are in a damp environment or not. Often they wouldn't be if they were being transported inside a rock in a meteorite or something. We also looked at iron tetraphenylporphyrin. It does some very interesting things which I won't go into in detail. But basically in the Martian environment, it changed a little, but not very much. We have this interesting double peak here for the Sorey band. And you can already see at 110 hours, it actually looks about the same. But after 1,700 and then 3,800 hours, it's really changing. If we look at the presence of water, again, hydroxyl does its dirty work, and we're degrading this to some species that we have some clues from our ground experiments what it might be. Okay, so what I've tried to share with you today is that you can do some very interesting fundamental science experiments in outer space with some really small hardware, not that different to what many of us use in our labs. And it's really the pushing forward of the frontiers by the kind of people in this room that have made this possible, because you couldn't have imagined doing such sophisticated fluidic biological growth experiments in a cube that size probably 20 years ago. That would have been quite tough. Integration and automation are a key part of this. Making the scientists and engineers work together is also very critical. Real-time in situ measurements actually are something that are hard to do on the International Space Station, but in this we're getting telemetry down every day or two, and so we really can see day by day what's happening. We can get the kinetics of what's going on with the organic films or the biology growth curves in near real time, and that's proved to be very, very valuable. Being able to do the experiments is paramount. We have more launch opportunities, less cost to do this than big space, and there's lots of availability of launches. So let me thank NASA Human Exploration and Operations Mission Directorate and NASA's Science Mission Directorate in particular, who supported this mission. I want to thank Dick again. It's been a great pleasure and honor to collaborate with him over almost 3 decades, two plus now, 2.5 and counting. We've done a lot of interesting things together, and I'm sure it'll continue. So thanks to all of you for your attention.
Okay, at this point, we're going to take a recess, and we will, if you have any questions for Tony Ricco, please, during the recess break, you can ask away, and we'll start promptly at 10:40.